second speaker is Mekoli. She is from the chemistry department at Iowa State University, and she's going to be talking about improvements in laser ablation, inductively coupled plasma mass spectrometry for trace forensic analysis of common household products using a short 100 femtosecond pulse ultraviolet laser.
Thank you for that nice introduction. And also I'd like to thank the planners and the NIJ for inviting me here to talk about my research. This actually was a collaboration by multiple people, I'll have to thank them later on. So a little bit of an overview about my project. We wanted to develop a method for use in forensic evidence analysis using laser ablation inductively coupled plasma mass spectrometry, or LAICPMS. And we wanted to compare nanosecond laser ablation to femtosecond laser ablation. And we wanted to use household common products that you might find at a crime scene, and focusing a little bit on the bomb-making aspects. And so we looked at duct and electrical tape, we looked at copper speaker wire, and we looked at galvanized steel pipe. So this is my instrument. It's actually the portion highlighted in red is our laser, and it's a schematic of our nanosecond laser. I have a schematic of our femtosecond laser, but for the sake of time, I'm not going to go through the nitty-gritty details of all of this. So please come see me if you'd like to see that femtosecond laser schematic. This is our Thermo Element 1 double focusing ICP-MS. Here is the plasma, so particulate matter or ablated matter from our laser will be swept into the plasma where it is atomized and ionized. And then after that, it's sent into the mass spec portion of the instrument. We have a reverse Near-Johnson setup where we have a magnetic sector and then an electrostatic analyzer here where we can actually discern between different isotopes of the same element. So why do you use LAICPMS in forensic science? Well, it boasts low detection limits, which are great for trace analysis. We can look at isotope abundances and even go as far to say that we can get a characteristic spectrum of whatever sample you're trying to analyze. The sample is destruction limited. I'm not going to say that we don't destroy the sample at all. We do, but it's very limited. And so this could possibly be for maybe the last analysis that you do on a particular piece of evidence. We can look at a range of sample sizes. There have been recent advances in laser ablation, but for our sake, we actually can only look at samples that are about, that fit into our laser cells. So it's about 2 inches in diameter. Some of the caveats of ICP are that your sample must be homogeneous, because if it's inhomogeneous, you don't want to be sampling the entire sample and just to get good statistics or a good representative spectrum from your sample. Also, quantification without having matrix matched standards is difficult, but recently we have been looking at using piezoelectric balances to overcome this caveat. So you might be asking yourself, why are we looking at femtosecond ablation? Because if you have a laser set up in your lab coupled to an ICP, it's typically a nanosecond laser. And here I'm trying to convince you that actually femtosecond ablation is the way to go. Femtosecond ablation boasts a shorter pulse duration, which makes the ablated particles smaller and more consistent than nanosecond ablation. And this leads to, actually in nanosecond ablated material, this can actually lead to large particles that are not readily ionized in the plasma. And you can get large spikes, and then your signal is off and your RSDs are off, and you have worse statistics. So femtosecond ablation actually has less heat transfer to your sample, which is especially good for the case of tape, which melts when you get it, anywhere near heat. And also, it's especially good for metals. And there are less fractionation problems when this occurs. So, can you tell the difference between these mass spectra? Well, you may be able to tell, to at least see or spot some differences by eye. What really matters are the analytical differences in the data. So to quantify these differences, I'm going to use principal component analysis, or PCA. So PCA is a multivariable statistical technique that first considers the variables, in this case, the intensities of your elements or your of your isotopes, with the most variance. So we're looking at the entire data set. And then it considers variables with the second most variance, and on down until you reach you've covered all of the variance. It gives a score, which can be plotted, and we tend to use software to perform this analysis for us. This approach is actually meant for a head-to-head or pairwise comparison, and it's not meant to be for attribution studies. So we're not looking to fill out a database. We're looking to compare two samples to one another. So the first part of the project was to look at tapes. And so duct and electrical tapes are often used in binding during a crime. They're ubiquitous. I can't count how many times I've seen duct tape in presentations that some of you have given. It's everywhere. It's a very good binder. And it can also be used in bomb making. So we sampled both the adhesive side, seen here, and the backing side, and we're looking at silver tapes in this case, or silver duct tape. So first, we have to establish that tape is homogeneous. And then after we establish that tape is homogeneous, then we can go and compare brands, or we can at least look at distinguishing between brands. And so what my method was is I took one revolution of the tape roll to expose a fresh roll. And this is actually advantageous for people who do the end matching studies, because that's actually our waste. And so we can analyze tape after the beginning of the roll has been, discarded. We put the sample on a large steel washer, roughly about 1 3/4 inches in outer diameter. And I cut off the excess with a razor, taking care to not contaminate either side. I would ablate the backing side, I would flip it over, and then ablate the adhesive side. For our homogeneity studies, I took 3 different samples per roll. So I would have, wherever after I exposed fresh tape, I would take a sample, and that I called the 0 feet. Go 3 feet down, and I called that the 3 feet sample, and then another 6 feet I called the 9 feet sample. So here are some of our instrumental conditions, and I'm actually not going to go over this too much in too much detail, but I would like to draw your attention to the raster speed. This is very rapid, and that's just because we don't want to to ablate straight through the tape. We don't want to sample the opposite side. If we're trying to sample the top layer or the backing side, we don't want to sample the adhesive side. So this is our femtosecond. These are our femtosecond conditions, and again, just note that there's a rapid raster rate. So this is the homogeneity study. This is a PCA plot. Notice how we have mixing. There are no distinct groupings at all. So in this case, we can actually say that the tape is homogeneous. Here's another brand and the other side. And again, notice how we have nice mixing. There are no distinct groupings. So we can also, again, say that the tape is homogeneous. So now that we've established that, let's look at the brands. Can we compare the brands? And this is a PCA plot of the brands. And notice how we do now have distinct groupings, and we can say that they're, differentiating themselves. Now, we need a little bit more of a statistical model to be able to say anything about this, though. So if you can imagine, we take the average of one of these clusters. So let's take the 3M brand, and we can take the average and say that we can draw a 95% confidence ring around that. And so my next slide, you'll actually see some data referring to these. So I just take averages, and I have a 95% confidence interval that the next sample you would take would fall within that ring. So this is our Q residual plot. And so here's our 3M. Now points, and here's these black bars are the 95% confidence interval that have been plotted. And points that lie below the line are indistinguishable from the particular method that we're looking at. So we create a method from the 3M data, or a model from the 3M data. And so you would expect in this case that the 3M data would fit the model that has been created specifically from the 3M data itself. And points that lie above the line are actually distinguishable to 95% confidence from that model. And so if we go through in each case, we can say that to 95% confidence, all of the tape brands are distinguishable from one another. So we looked at electrical tape, and I'm going to kind of fly through this because now that you know how to read these charts, it'll go a lot faster. So here is our PCA plot for the homogeneity study. Again, note that we don't have any distinguished groups. There are no groupings. They're all pretty mixed. So we can say that the electrical tape in this case is homogeneous. Again, note that we have some very tight clustering between all 4 brands. I actually was looking at 2 different brands of Super 33. One was probably from the 70s, has been around since before I was born. And one of them is actually a very new role. And notice how they actually do differentiate themselves in the PCA plot. Here's our Q residual plot, and the take-home message from this is just that all brands are distinguishable to 95% confidence from one another. So let's switch gears and look at copper speaker wire. And copper speaker wire can be used in binding for a crime, and again, also in bomb making. So how speaker wire is actually made is that they take multiple rolls of these thin copper strands, and anywhere from 10 to 15. And they're all on individual rolls, and then they're kind of wrapped and twisted together, and then they're coated in a plastic coating. And so what we did was we removed the plastic coating, and we separated individual strands within this bundle of strands. And I'm really glad that I wasn't the student that did that, because it took this particular undergraduate about, 3 months. So I can say that I'm quite glad that that was not my job to separate these strands. Then we had one of our summer students actually make this device, and so this is just meant to keep the wires straight. And so we would mount these individual strands onto this device, and then we would do single line ablation using our nanosecond laser. So this is the data that we got, and I know it's kind of cluttered, but also actually, before I say anything about distinguishing these, within the 8 feet of wire, copper wire that we sampled, within the strands, the small strands, they were all homogeneous. And so now this is comparing the wire strands to one another. And the take-home message here is just that every single wire strand can be differentiated to 95% confidence. They are distinguishable. Excuse me, let me rephrase that. To 95% confidence, every strand is distinguishable from the other. And this is actually advantageous because if we compare, say, one particular brand to another, now we have not only one-dimensional data for one particular strand, we have multi-dimensional data from multiple, from the entire bundle. So this is very advantageous. So we could possibly compare that bundle to, say, another manufacturer's bundle and try doing that. Actually, that's our next step in this project. And so we also have just dabbled a little bit in galvanized steel pipe. Again, this can be used for making a bomb. I understand that PVC pipe is more common, but we also wanted this to be a representative material for bulk metal analysis. So this steel is actually mostly iron, and the coating is a zinc coating on top. And this coating can vary by manufacturer conditions, such as the number of times it's been dipped, the cooling time, the cooling temperature. And so possibly we could go back and do a layer-by-layer analysis and see how thick these layers are. So what we did was we took pipe, cut it into pieces. We did a line depth profile with a nanosecond laser. And so what you'll see in the next slide is basically as we ablate a line, we'll ablate a line, then we'll ablate over the same line and again and again. And so you'll see kind of as we go down deeper into this trench, we can actually look and see what are the major components of this pipe. So here's our depth profile using our nanosecond laser. We just looked at 2 isotopes of zinc to make sure that we were indeed looking at zinc and not looking looking at interferences. And so what you can see is that going from the top down, as each successive line is ablated, we can see that the zinc increases, levels off, and then decreases. And the iron, which is underneath the zinc layer, constantly increases. And so this is useful for doing a layer-by-layer analysis instead of dissolving the entire pipe and looking just at what's in the pipe. So some of my conclusions, electrical and duct tape are homogeneous within a roll. Tape brands may be distinguished from one another. We saw that bulk copper speaker wire bundles are homogeneous within the roll, and individual copper speaker strands, speaker wire strands can be distinguished from one another, which could allow us to do attribution studies. And then galvanized pipe coating depth may be sample, which could allow us to do a layer-by-layer analysis. And just some acknowledgements. I'd like to thank the NIJ for funding this grant. Dr. Sam Hauk and Stan Beich, who are my PI, or who are the PIs for this project. Jonna Berry did the copper wire. Maria Bach helped me with the tape. Janae Jacobs did the galvanized pipe data. And then Dan Zamzow, who is kind of our femtosecond laser guru in the lab.